I'm Andreas Fertig, and the title of my talk and the topic of my talk today is Embedded Friendly C++ Features That Make a Difference, hopefully for you too. A few words about me. I do a lot of C++. I'm the creator of C++ Insights, a tool you might have heard of. I maintain a YouTube channel where I host at least monthly videos, mostly targeting topics about C++. Using C++ Insights, I'm an author, so I wrote a couple of books, but my main business is teaching. I do in-house or corporate training, however you want to call it. So if you want to learn with me, I'm available for in-house classes, remote or on-site, whatever suits your needs best. If you want to look into learning more as an individual, I also offer self-learning courses, so you can study anytime and at your own pace, which usually is very convenient. I happen to be not from Berlin, but from Germany at least. My last name, Fertig, is a very frequent occurring word in the German language. You can translate it to ready, finished, complete, or completed. And I just recently realized that the word itself carries as well as the begin as the end. So you can ask somebody whether they are ready, and you can ask somebody whether they're completed, which also leaves a lot of room for people not really knowing what you're asking for if you're asking whether they are fertig. So maybe I'm already fertig with the talk, which means we all can go now, or hopefully the better choice for you, the talk is ready, so prepared and fertig to go. So the latter is the case, which is good. I decided to not just show you random code snippets for this talk. I'm more looking towards telling you a story. So let's imagine we are all developing some embedded system. It's not really in this room because we don't have light bulbs, but let's reduce it to something really simple. Light bulbs nowadays are not as simple as they used to be. We can control them remotely via network, Bluetooth apps, or whatever you have. You can change the color, the shades, the whatever temperature, and so forth. So not necessarily a simple system anymore. And everything good? And we want to look towards implementing some system that controls your light bulbs. Still very simple, so we will not have a working prototype after that. But this is the rough idea. So what I have for that is a couple of data types I like to share up front. So since we are talking network communication, this is something I did a lot in the past, we have a network, a MAC address to address our devices on the network. I use this struct here, which wraps around a std array. That way I have a strong type MAC address. It's the address of your network interface card, in case you have never heard of that. 6 bytes. And if you print it out with something like ifconfig or ipconfig, you usually get the numbers formatted in hexadecimal, separated by either dashes or colons, depending on the favor of your operating system. The next thing we have, since we are embedded and we are dealing mostly with colors, right? Color shades of the light bulb. But the color levels, usually we can specify something in the range from 0.0 to 1.0. So floating point number for RGB. One particular thing we know about that is we never will exhaust the entire range of a float, neither float nor double. But we need something with a little more precision than a regular integer. So I introduce an FP16. So a floating point value with just 16 bits. So if you're looking at a regular float in IEEE 754 conformance, we're talking about 32 bits. So I cut it down half because this is essentially what I need. And I want to save storage space as well. So this is my next struct. And in C then, I'm composing this FP16 struct to my RGB and the alpha level in a struct called RGB color. So I have all of them now in a set. And then we have the most awesome protocol I've ever wrote, and believe me, the parser for that will be real simple. The protocol enum here, it simply says update. We have no clue why this update is coming and where from and how to react on that, but update, this is the one thing. So we keep things simple today. I use a class enum, and I use the opportunity to specify the underlying type as a uint 8t. So I wrote that one in stone. And then we have basically the heart of everything here, this light bulb control structure. It contains the MAC address for my light bulb, the RGB color, and the brightness level. So these are the things that essentially later changed my light bulb. Now, whenever you're doing networking, or you've done in the past, you might know that, I think I never seen it, that one customer or in one company, you had just did one architecture. So usually you have a couple, and if not in the beginning, you end up with them later. So you might have big and endian machines, you might have 8-bit, 16-bit, 32-bit, 64-bit architectures. That means things like padding and aligning your data structure here to the right level comes into play. And you want to make certain that once you laid out your data structure, considering all the layouts and all the different architectures, so it's perfectly aligned on all of them, nobody inadvertently changes it and corrupts things. So one machine thinks it reads a color, but instead it reads 2 bytes off and you get half a color. How can we achieve knowing that there is no padding in this light bulb control structure? And this is a simple type trait that came in actually with C++ 17. It's called has unique object representations. And I use it together with a static assert to assert that my light bulb control structure indeed does not carry any padding. So this is one way you can at least make certain that all the efforts you put in once will be honored in the future, and if somebody violates them, well, at least they get a heads up and can do things accordingly. So this is something C++ 17 did for us. What's next? Oh yeah, we have the light bulb itself, right? And we have a real basic class here. My light bulb class here contains the RGB color as a data member and the brightness level as a uint 16. It comes with a constructor, that one, no surprise, takes an RGB color and the brightness level. And since we can change all these things later on, the constructor does not explicitly set the data members, but instead it defers that one to an update function, because that one is called later from the outside when the class already or the object's already created. So that's great. And if you look at things, then we can see I chose to make the constructor const expr because I'm on embedded and even not on embedded. I want things as efficient as possible, so I want that data structure, that class, be able to get created and laid out in memory at compile time. Now I have this update function, and the update function itself is const expr as well, so we are technically good to go. And with this code, as I'm showing it here, we are really good to go. But I'm trying to showcase here something that happened to me a lot in production code. I have this update function, and yes, everybody wants it as efficient as possible, but sometimes we want to get some glimpses inside. We want something that people call debugging. Others say it's not debugging because it's just printf and it doesn't involve an actual debugger, but it helps us to get a feeling what the code might do, especially if it runs really fast on the network. So I have here in B this std print line, which by the way is an awesome thing we added in C++ 23. All the other languages that had similar things before, they will now look real bad because C++ has it too. So Python, C#, and all how they are called, now we can have a format string with just curly braces in it, and it gets formatted accordingly and properly. It's type safe, it combines printf and std cout, so you have the format string, but you also have the type safety. The empty curly braces will fill in the correct formatting for your type. So somebody discovered that cool new feature and used it in my code, and they say, well, we don't want to give that one up. We have sympathy for you that you want to run things at compile time, but we run things at runtime. And let's face it, the runtime part might still always be the larger one than the compile time part, so they might be right. This was one of the biggest obstacles in writing const expr code in the past, because the idea is to be able to switch between the two worlds, but then we have some constructs that are restricted to only the runtime world. And what I'm showing you here in A now is a C++20 change, the if const eval. And that helps you to say, well, either that code is in only at compile or only at runtime. So you can add an else case to it. As you can see, there is no room for parentheses. So there is no condition to the if const eval, because the if const eval carries the condition in its name. The question is, are we executed at compile time or not? The only thing you can change, you can add the not, as I did it here, or the bang operator, the exclamation mark, if you want to negate the condition. And you can put an else case to that. So that's all you can do here. But this helps me now to say the print line, which obviously is runtime only code, it's not present at compile time. So I can run this entire code at compile time and only the printf gets discarded. But I have the ability to run it at runtime with the printf included, which is really cool. Now I have all that. And in C, at the very bottom, I'm creating a light bulb object called ceiling. I initialize it with a couple of values. And now the next part came in. I provide everything that's required to evaluate that thing at compile time. But if I make the ceiling object const expr, I can't update it anymore. So you would have something like a very fixed colored light bulb that technically you could control via the network, but it will never change. It might be $1 million idea. I've never run it by anybody, but I doubt it. So C++20 once again helps you out here by providing a new keyword called const init. So that means constant initialization, but if you compare it to a const expr object or const expr variable, it does not carry the const that usually gets added to a const expr variable. So that thing here ensures that your object gets initialized at compile time, but you can still change it later at runtime. So this is what I want here. I want to guarantee that that thing gets initialized at compile time, but of course, it's the thing we are developing, and the idea is that we change it at runtime, so let's do that. So this is what const init here gives you in C++20. Guaranteed initialization at compile time with the option to change things later. Cool. We have the MAC address, and that means we need to create MAC address objects. I showed you the struct before. I mean, it's just in std array, but we need to get somewhere to this std array. So how to do that? Usually we start by maybe the user putting in a C string literal-like string, or we have one in the code base already for a couple of well-known things. So here in A, I show you another addition from C++20, the std2 array conversion function. So you can feed it anything, and it creates you a std array of the type with the individual values in this array set. So now I have a fixed sized array at compile time that I can use. And I offer two options to now trigger the actual conversion. One is calling a function called macFromString. So that's my actual conversion function. And sometimes it's just nicer to have a user-defined literal like in B here and provide a string literal, put the user-defined literal MACAttr to it, and let it do the conversion. So these are my two things here. Let's look into the conversion function. And the goal is not to spot bugs here. I'm fairly confident there are none in, but I wouldn't risk it. It's more looking at the building blocks I use to compose it. And if we start at the very top, at the very beginning, with the return type in A. So the return type in A is a new type that came in with C++23. It's called std_expected, and emphasizes on the positive thinking here. We are expecting a certain value of a certain type. And this expected type is the first one here. It's the MAC address, so this is what we expect by default. You can see it like an optional. An optional you can type, and you can then later ask, is the value present or not? And if the value is present, you can fetch it. The issue with optional in some cases is if the value is not present, the not present information might not be enough. You might be interested in the why is it not present, what failed. And the optional only tells you, well, it's not there. Do something with it. Or better not, because it's not there. So the std_expected therefore comes with a second type in its parameter list of the template, and that's the error type. I picked std_error_c here, the std_error code. You can put in everything you want, you have in your code base, whatever is a type that gives you the information you need for pursuing when that call failed. The nice thing here is you have basically a way to get rid of the POSIX API where you return -1 for that was an error condition and set an error value or other stuff. Return a bool for false, the operation failed, and then with an out parameter what the actual error was. Here you have everything in once. The std_expected works like an optional with the additional information of why it's failed. So you either have the size of the error code or the size of your actual return object, return type. They are seen as in a union. You pay only for the larger of the two. The two are overlapping, and either the one or the other one is active. You can ask whether the expected has a value or whether it has the error condition. And if it has a value, you can fetch the value. If it has the error condition, you can fetch the error condition. And of course, you cannot do it the other way around because the value would not be there. Why is the std_expected such a helpful thing for more than just your code in writing? It's also for the maintenance part, for the review part, for the working with it later on part. Because if we look at things like C that I marked here, if you hit an error case, you don't construct a std_expected directly. You construct something that's called std_unexpected. So that's your failure path. This results in a std_expected getting created with the error value, but you can spot the places very easy now in your code base where you return an error opposed to the happy path. So that's something that I appreciate a lot here. Going up back again, the second new thing here in B came in with C++20, one of my favorite data types potentially. It's a std_span. A std_span is, you can compare it to a untyped string view in C++17, so a std_span can take more than just a const char star, can take any type you want and a pointer to that to an array. So I use it here with a const char, but it could carry more than that. You can ask it about its size, you can use it in a range-based for loop, very much like a string view. So this is your more versatile version of a string view for all other data. And especially parsing here comes in really handy. You can create a subspan, for example, down here. You can access values with either the array index operator or, as we will see later, with a addMember function. So this is the more C++ style to maintain your C-style arrays. The nice thing is you can create a span from a C-style array and from a std array. So this is the bridge thing that we were missing to go more type safe and bounds checked, because now you can create a std array on the stack and your function simply takes a std_span of that type. but it does not need to carry the size around like the std array initially did as a template parameter. It knows it by a runtime parameter at runtime. Now, the thing that's missing for now is the user-defined literal operator that I have here. My Mac adder literal operator, I picked a version where I take a const char star and the length, and internally I forward to Mac from string. I create a span with the pointer to the string and its length, and, well, call Mac from string. And directly, without any checking, I'm calling value. Why? Because I never make a mistake and I know it works. No, not the truth. The truth is, because that function here is const eval. My user-defined literal operator uses a new keyword from C++20 and the new feature by that, which says that this function runs only at compile time. You might also find it referred to as an intermediate function in the standard. So opposed to const expr, which is dual, can run in both worlds, a const init function can only run at compile time. And since I know that if I access value and it would throw me an exception because the value is not there, my compile would terminate. So this is why it's safe even if I make a mistake. Otherwise, you shouldn't do that. You should check with an if whether the value is really there. But the const eval here is another tip. So I would make all user-defined literal operators in C++20 and onwards const eval, because they are actually only your proxies to create something, and that should happen only at compile time. And by that, you also might be able to outsmart the colleagues that think and know that they can invoke the user-defined literal operator by hand, right? Because it's just an operator. So now they at least can't anymore at runtime. Oh yeah, we had this FP16 number, right? And I don't really want to go into all that code here and whether the conversion is correct, but it's a lot of this bit shift stuff that you might love, like, or hate, whatever it is. But we are trying to compressing the 32 bits down to 16 bits. We are throwing away a bit of the mantissa and reducing the characteristics and the exponent by that. But we keep the notation that the highest bit, the most significant bit, is the sign bit. We also follow the order of the IEEE 754 standard. That's all right, and we check for overflows and underflows and the rest of the function. The major problem, the major trouble starts in the first line here in A. The task is I get my float, a real float, like it's baked into the language. And I want to grab its underlying bit representation. A very natural thing, so you teach that at a university to, I don't know, second-year students or something like that, first year. So we want the bit representation. And the natural thing to do that I have seen done a lot in the past is to say we want to reinterpret the float to a uint32t, for example, because we know it's 32 bits. So we use reinterpret cast. We have to do a couple of nasty things. We have to fetch the address from that float and say we reinterpret the address of the float to a uint32t, and then we dereference that and write the result into a uint32t. And we are done. And actually, it's a little like the upcoming Christmas. It can be a bag full of surprises. It might work, it might fail later, it might fail never. It's undefined behavior. This is not what reinterpret cast is there for. Because you're starting the lifetime of a new object, and the reinterpret cast option is not to do that. So this is undefined behavior. Despite that it might work, maybe your compiler even documented that it's legal. So you can do it, but from a standards point of perspective, it's undefined behavior. But there is rescue. Smart people figure out different ways. So the other way is to use a union and do type punning. So we have a union with two data members, your float and a uint32t. We create this union or an object out of this union with providing the float, and then we are reading out the integer. Because the two overlap, so if you write the one and read out the other one, we get the underlying representation. That's sweet, nice, and easy, and I'm not even sure 100% whether this is legal in C. I'm on the fence to saying it's illegal in C as well, but it's for sure not legal in C++. So it's undefined behavior. Option number 2 seems to be a no-opt as well. Same bag of surprises. It might work, it might not work. GCC, for example, documents that if you turn, I think it's strict aliasing on, they support doing this stuff. I'm not sure how far they go, but at least that simple case and in documentation is supported. From a standards perspective, it's undefined behavior. So we have to be careful. But what else can you do? The two favorite options that usually pop up, I just told you shouldn't use them. Well, you can go to C++20 then. In C++20, we added std_bitcast. And the purpose of std_bitcast is exactly providing you what we all the time desire to do there. We want to take one object and use its bit representation to create another object. So there are certain rules, so they have to be the same size and trivial and so forth, but this is what you should reach for if you have C++20 on your hands, because then you have the guaranteed by the standard undefined behavior free version. So this is something that C++ did for you, and this is a task I can tell you that I've did a lot in the past, and I got a lot of surprises. The other thing, and I like to apologize for the example, I know it's this classic enum to string thing, but this is not really my objective here to teach you that. If you really want to do a cool enum to string version in C++, go check out C++26 and static reflection. It's purely awesome and it's really great. No hackery, no tricks. My point here is a different one. Let's say I have the issue here. I have color parts with red, green, and blue and alpha because at some point we want to present to the user these certain values and the user wants to set the values. So they need to know at some point which of the columns is for which value. So we need to map them. And my getName does that. I have this constexpr variable here. It's a std array of std string views of the strings red, green, and blue. And I use the addMember function here from data to grab the correct value. Yeah, the next thing is, right, to really do that the right way, you have to write this longish, beautiful static cast. So you have to fetch the underlying type of your enum because you never know what the underlying type is. It's either what you specified, or if you didn't specify, it depends on the largest member in your enum. The std underlying type T type trait in the standard library helps you fetching the type, and then you're saying, well, I'm casting this parameter value now to this type with a static cast, and then I have something that I can use to grab the value from my std array. That's the correct version to do it. So that code we can say is all right, it's good, it's working. There's one drawback. I tried to be good, and I made this object here my data variable on the stack constexpr. So that one gets initialized at compile time. It's laid out in memory, all good. Problem is, it's inside a function. And what you're getting back is just a const object inside that function. Now, if we would call this function recursively, the standard guarantees you that in each recursion step, this variable data has a unique address. So it gets put on the stack for each recursion step you're doing. And the compiler would have to prove to you that you're not doing a recursion. Only then it can provide you only one address for that. And otherwise, whenever you're calling this function, you're now risking that, yeah, you have the data laid out, but it gets copied on the stack. So you're paying with the copy, not necessarily with the initialization, but with the copy. The better way to do this would be, if you bend the guidelines a little, like Misra, make this array static, because this is the guaranteed way that it remains only once in your binary, and this is what you want. But sadly, you cannot have a static const expr block local variable inside a const expr function. That's not permitted. Before C++ 23. So C++ 23 finally allows you that, and now you can combine the two worlds and can express what you always wanted to say, and this is that variable here in my function that should be initialized at compile time and executed or existing only once. So then you do not get to pay for the initialization all the time you're calling the getName function. And as another help here in B, you can see we also took care of that beautiful static cast with the two underlying type. All my money for teaching goes away if we make things so easy, right? Because now there's a two underlying function in the standard library in 23. So things really can become easier. I make myself obsolete with such things. Now the hardest part is receiving and sending data from the network. We are focusing solely on receiving. We only have the update function, right? So I have this small function receive here. Receive takes a studspan of unsigned car data, and then it checks whether the first byte in there is equal to the update value in my class enum. And if so, we are totally happy. We say we call a function called process. Process here does a dance. We're saying, oh, we reinterpret cast whatever we got in this data here at the second position to a const light bulb pointer, and we dereference that thing later on. And now for all of those whose day wasn't that long, you might be seeing that this is the pattern I already told you. It's UB earlier when we tried to convert the float to a uint32t. And this picture doesn't change here. What changes is the solution that I showed you before, the stud bitcast, might not be the tool you're looking for here, because whenever I did networking, I was basically looking for 0 copies. So your stud bitcast, the solution I presented for the float, that created me a new uint32t, and I stored that one on the stack, and I was happy in that scenario. Here I'm receiving data from the network. I don't want in each intermediate step to put that data on the stack and copy things around. I know that the other side, I believe at least I know, that the other side put in a light bulb control structure there. So I really just want to reinterpret cast that. I don't want to make a copy. This is what I wanted to express with the reinterpret cast here, which sadly I showed you is UB, so this time we are not even going to talk about the union version because that one is UB either. So what can we do? We can use C++ 23, and if you get your hands on a very recent version of GCC, then you can for the first time really try this out in practice, because until I think 3-4 weeks ago there was 0 implementation for that. There is a start lifetime s function in the standard library, and the sole purpose here is to give you what you wanted in that scenario, give the compiler an understanding that we want to take this set of bits and bytes here and simply reinterpret cast it as a different type. There are, again, certain limitations to that, so it has trivial and so forth. You can't have virtual member functions in there and other things, but this helps you to get from one representation to the other one. So we can, for the first time, implicitly start the lifetime of such light bulb control object at a place where other data already exists and reuse the bits and bytes that are already there. And with that, you can achieve a 0 copy version here. So this is or these are the two tools that you might consider. First one is bitcast if you want to store it in a new object and are fine with additional storage space or even require additional storage space, or you can use start lifetime as if you say you want 0 copies, but you know everything is there and in place and started. So that's a really great thing, because all the other solutions where usually you might find a few that tweak around that, but this is the perfect solution here, added with C++23. You have also a version for the array syntax, and I'm happy to take questions after the talk. It's fine. You also have a version for arrays, so everything should be fine with that. Now we received the data, so let's process it. And processing, boy, that's fun, because I pointed out earlier, we might have different architectures. So when I started years ago using an Apple here, I bought one of the last PowerPC iBooks. And then they switched to Intel. And PowerPC was big endian, Intel was little endian. So some of the things weren't as compatible as they are. Now they switch back to ARM, so I have the third generation of CPUs, which is fun for another reason, because Compiler Explorer, for example, shows you x86 assembly. And I'm running it in a Docker on an ARM machine, which at the moment works. So things are funny. But if we do networks things here, then that means we have the, well, standard to send data out in network byte order. And network byte order is defined as big endian. So you can, of course, inside your own network, inside your own company, decide differently, but that's usually the rule. That means every little endian device, which I think is the majority nowadays, has to convert all the data from little to big endian, and the receiving side does the reverse, if they're little endian machines. So this is what I'm doing here when I'm calling ceiling update. I swap all the data. And if you're under Linux, POSIX, then you know this htons or ntons, ntol functions, and you might have experienced a lot of fun if you mess up the L with the S and provide the wrong data type. Well, it works in some sense, but it swaps to partially the wrong data or the other colleague's data, so why should I care? It's theirs, right? So usually we have in C++ some wrapper around that to make it more type safe, so I call this function swap. And now here comes the real beautifulness. You can combine now a couple of things. You know C++ 17's context if potentially, so that says we do this thing only if the condition is evaluated to true as at compile time, and then only this branch goes in, and otherwise the branch doesn't exist. And now we can combine that with a C++ 20 edition, which tells you the endianness of your device. So you have little and big endian for all the middle endian folks. Sorry, I think that's not included anymore, but that was fun too. So we can compare whether our native architecture is equal to little endian. And if that's the case, because I'm expecting network byte order coming in, then I use from C++ 23 a stood byte swap. So no POSIX htons stuff anymore. We have it all built in and baked into the language now, or at least in the standard library. So you can go all C++ now, and you don't have to find different solutions if you're developing code for Windows and Linux, for example. Stood byte swap to the rescue. So that's good, right? We received the data, we swapped it. We have the MAC address cover, the floating point, all nice and sweet. What else? Yeah, maybe we wanted to write this config down at some point or read the configuration, because if somebody actually turns off the light bulb and it boots up again, we might want to have the same settings. I have one in my office that I think it says it's smart. I haven't figured out why, but usually after being away for a while, so like attending a conference, it loses its settings or decides something else. It manifests in a way that it goes back to the default color, which for some reason, maybe to understand that it's not the normal, is all red. So I turn on the light and everything is red. It's not even bright, so you can't see a lot of things other than it's red, so it's brilliant. Never figured out why they're doing that and why it loses its information, but it does. So we want to store or read the data, and I like to do things the C++ way, so RAI, resource acquisition, is initialization, right? And I use a unique pointer here to say, okay, I have opened this file, I store what I've opened returns me, which is a file struct, so file, uppercase, everything. And for closing, I have to call fclose. So I can teach my unique pointer to do something other than delete when it destructs. So in my case, it calls fclose. We could say case closed. That works. It's not beautiful. It opens the scope for too many mistakes. So the first thing is we have now to provide a signature to the unique pointer that says it takes a file and a decal type of fclose. Because I can't remember what the exact function pointer signature for fclose is, does it return void or an int? I always forget, and I don't care in this scenario, so I use the decal type. I provide a custom deleter here, but once I start providing a custom deleter, I have to provide this function that's then called. So this is second parameter to my actual unique pointer whenever I construct one. So I have to say I have opened that thing and I provide you a pointer to fclose. This is your delete function. Users can forget that. Users can provide something other than the actual fclose, which in some cases can of course be good if they want to log and then actually close, but it could also be that the file never gets closed. And we have 2 instead of 1 parameter, so more isn't better in my opinion here. The next thing is it gets less efficient. So usually we teach that you can use a unique pointer as a replacement to a raw pointer because it's just a small abstraction around a raw pointer. But if I do a static assert with the size of a object of this unique pointer, f here, then that assert only passes if I say that f is greater than the size of a void star. So essentially greater than the size of 1 pointer. And the precise value is it consumes the storage space of 2 pointers because it has 1 pointer to store the actual data and a second one to store a pointer to fclose. Which might be good if fclose is a runtime property, but fclose comes from the library, it never changes, the address is baked into some kind of library, so I don't really see any benefit of carrying around a runtime value that never changes, but I have to maintain. So a lot of drawbacks here. What can we do? We can use C++20, and you can write it differently, right? This is a very generic version that you could deploy in your library in your company. So I use a templatized using alias here. I call that one unique pointer deleter. It takes a type name t and the C++17 auto non-type template parameter. So that one will become a function pointer later. And I let this using alias point to a regular unique pointer. That unique pointer takes the t, as it always did. And as a second template parameter, I provide a decal type. And in the decal type, I now use a captureless lambda. That captureless lambda takes a t star and calls the delete fn passing the parameter obj here. Only since C++20 you can use decal type to a captureless lambda, because only in C++20 and later you can apply decal type to unevaluated objects, and lambda is unevaluated in that case, and since it's captureless, there's nothing that's going on if that thing becomes alive, so there are no data members. So this is the perfect thing. Now I have this little tool, unique pointer deleter. You can give it a better name if you prefer to. And now my users can create a unique pointer deleter and say, this is for file, and the closing function is fclose. So it is a little like before, but the major benefit is the actual creation, the constructor call of this unique pointer now, it takes only one parameter, the result of fclose. The other thing that I did is I shifted things around. This gives the implementation the opportunity to utilize another thing that we had in C++ for a very long time. Whenever you have an object without any data members and you size off on that one and ask for the size, the compiler returns you 1, at least 1. Because in C and C++, every object needs to be addressable. And for being addressable, you need a storage size of at least 1. Even if that thing is empty. So it's like Schrödinger's cat. If you ask it, you get an answer, and if you don't ask it, you might not know. Or you know because you didn't give it any storage space. What implementers then realized is we can do something like saying, all right, I have a base class that's empty, and if I derive from that, if somebody asks for the size of this derived object, we don't need to add +1 because it's already addressable if your derived object comes with at least one data member. So you can have an empty base class. This is also referred to as empty base class optimization, EBO. And what your standard library now one way or the other does is saying, well, if instead of providing a pointer as a deleter to your unique pointer, you're providing a class type, we behind the scenes technically do something like, well, then we derive from that type and save you storage space. Because the information is already present, there is no runtime part on that. And this is why the static assert here now says that it passes if you ask it that the size of f is equal to the size of a void star. Because now your unique pointer really only stores one pointer, as you desire potentially to do so. So we did good. Question is, can we do better? So is there something left? And this time we are really looking for tweaking the last assembly instruction that might be there, right? There's something that's not really maybe apparent here, and it's a little hard to prove whether it helps or doesn't help. But from a pure standards point of view, the lambda here, you know what's behind the lambda, it's a class, right? The lambda's body is the call operator inside that class. And like for every other non-static member function in the class, the first parameter to this class is the implicit dispointer. Every non-static member function in a class carries an implicit dispointer. We now know something very precise about this code, about this lambda. That dispointer is never ever needed because there is no data member and there is no other function, there is no real object for this specific case when we have a captureless lambda. Once you have captures in there, everything changes. But for captureless lambdas, the dispointer isn't required. It's never used. But the compiler has to make sure that the call signature fits, that your ABI fits. So it has to prepare a dispointer, prepare the register. Even if it's just with garbage or with 0, it doesn't matter. It has to do it. Unless it can prove that all call sites don't expect this pointer being called there, right? So one thing that you now can make better if you go to C++ 23 is, say, we make that call operator a static member function. I'm only showing you the static here applied to a lambda, but in C++ 23 you can make every call operator and every array index operator static. And this is why it's also working for lambdas. In lambdas, I think it's the most interesting part because of the syntax. So where do you put the static? For the regular member functions, you put it in the same place as always for all your member functions. Now you flip the switch, you told the compiler that this thing is a static member function. Compiler now knows it never takes a this pointer, an implicit this pointer. So it can save you between 1 and 3 assembly instructions, or 0, depending on your optimizer setting. So if you really want to go for, as I said, for the last instruction to squeeze it out, that might be something that you are looking for here. All right, perfect. So we have a all-rightish working system here that converts us and works with the light bulbs. And sadly, I don't have the control over the lights here. It would be fun now to turn them all off and say, thank you for listening. I am Fertig. Thank you. Thank you. So we still have time for questions. Do we have a microphone to pass around, or shall I repeat the questions?
Sorry for bothering, playing the standard devil's advocate. Taking the address of a standard library function is usually undefined behavior, and yes, you might know that. So the example is a little bit cheating. Fclose isn't addressable, so you're actually not allowed to do what you showed directly. One minor thing, an alternative to static, if you don't have C++23, is just instead of using auto for the unique pointer template parameter, to actually use a function pointer there, and then pass the lambda, and it will degenerate to the function pointer, which everybody can observe perfectly in your tool.
Yeah, agreed. Thanks, Peter.
Hi.
Hi.
Hi. On one of your earlier slides, where you showed stood expected, you said it would be C++23, but the slide said C++20. I guess the slide is wrong and it's 23.
So I assume you're talking about that one, and my way out is to say that in this case the slide says it's the smallest standard because span came in 20, but stood expected is 23. Yeah.
Okay. Does stood expected use any new language features, or is it just library functionality?
It's just library.
So one could backport it to 20 if needed.
Yes. Yeah.
And I have another question, and that's about that stood bitcast and the start lifetime as. I think there's a core guidelines rule for it, and it says that you could just use stood memcopy. Of course, you have theoretically you have a new object, but I think there's a video by Jason Turner where he shows that the compiler just removes it and just says, yeah, people just want to do a safe reinterpret cast here, and just drops the copy. But I have a different question: isn't stood start lifetime as isn't just a new name for a reinterpret cast?
No. So two things here. If you are potentially able to use stood bitcast, you don't need to do the memcopy solution. The thing is that technically memcopy was wasn't really supposed to create new objects before C++20. It was applied as a DR to older standards. So this is why you can even use it in C++11, given that you have a compiler that implements it. Otherwise, it's technically UB. I think no compiler ever exploited that, but that would be the answer to that. The start lifetime as is a different thing. So reinterpret cast, the name might be wrong for that purpose, but from the abstract machinery part of view, we need to start the lifetime of this object because we are in C++. And once we want to receive the data and say, in that bits pool here, we have an object, the abstract machinery, your compiler, more specifically the optimizer, must understand that there is an object there. We usually have constructors for that. Since C++17, memcopy does also start a lifetime of an object as memmove does. But this is the trickery here, and the most, I'm not sure whether the most, but one major reason why start lifetime as here came in is that most of your implementations with reinterpret cast work, because your compilers are somewhat agreeing with you that this should work. But they have a hard time to fight with their optimizers. Because for an optimizer, this is UB. So they have the difficulty that some optimizations, they have a hard time turning them on. They're not there to exploit your reinterpret cast in that scenario. But it might do because they targeted something else and it looks similar. With the start lifetime as, the standard gave you a way and the optimizer to say, this is the way to do it. We don't optimize that away. You started the lifetime of a new object, we respect that. And with that, your compiler vendors now have a free card to say, all right, all the other use cases, we can identify them as UB. And we can rightfully remove them and direct you to lifetime as if you argue that your code should work.
So I would summarize, they could have fixed the UB of reinterpret cast, but they weren't sure if they could do it.
No, they couldn't fix it. So reinterpret cast is there to do something else, period. It's just that the optimizer allows it.
Yeah, just as an answer to
Christian,
there is an implementation of stud expected in GitHub. I don't know off the top of my head. I compiled it in C++20, but I think it will compile at 70, C++70. I'm not sure, but it works quite good. So it's very nice. So I don't know it, but I can give it to you.
Thank you. I'm not sure, Peter, maybe yeah.
Thank you for the talk.
Welcome.
I wanted to ask for people who don't use GCC 3-week, which is the 3-week-old, am I able to correctly implement using C++17, 20, 23 the start lifetime s function until I get it from the standard library? Did the language rule change, or is it implementable?
That's a tough question. There are slides and code out there that show you how to do it. First question is, do you desire to support all use cases? So it's a little easier if, and this is why I picked this version here, if you do it on non-const data. But I'm doing it on const data. So that means you have to start a lifetime in a const object region, which means you have to cast away the const, create the object, and then return it. So I've seen implementations, whether they are really working in all scenarios, I can't say. If you look at GCC's implementation, as far as I understood it, it's basically something like a memory fence that tells the optimizer that this bunch of bytes is used and it doesn't understand how, so cannot optimize it away. So they're really doing it in assembly. And I'm not even sure whether this, so I assume, but I haven't verified that it runs on all architectures. But they did it on a very low level. And for LLVM, for Clang, I saw a discussion thread that they request new support from the compiler, so they think they cannot do it in the library alone. So that would be my answer. So you can potentially, but maybe not.
One last question from the online audience. Could you go back to slide number 10?
Oh, thanks for remembering the slide number. Yes, here we are.
Can't we use a struct of union with a flag mentioning the type and union of types? would that avoid UB? Used to use this way in C, if I remember correctly.
So C might be a different plate, as I said. I read a discussion from the GCC maintainers. They claim that it's UB in both languages. Yeah, Peter, I know, I'm not sure. I think the reading is that it's legal in C, which is part of the pitfall here. But the problem is that even I think with this solution, you start reading a non-active member of the union. So this is UB, you cannot read the unactive member. So by that, maybe if you send me the online audience, if you send me the code later, I can check it. Maybe I misunderstood it, but I don't think there's a way to do that. Peter's maybe a final comment?
In C++, it's definitely UB, except for very few cases, like having a byte array and things like that, and you can access those things. In C, it's used throughout almost all embedded systems for type hunting. So even if it would be UB in C, compilers will never make it not work.
Yeah, which partially
that's why people get easily confused. In C++, it's definitely UB, and compilers will cheat you on that.
Yeah.
And I've reviewed code in C++ trying to do the correct thing, and they were still wrong. So it's easy to get it wrong.
Yeah. And if you
I tried once to make it right, but I'm not sure if I did it correctly.
Yeah, because what Peter said, if you want to follow up on that, we have one rule out of that, and that's a common initializer sequence rule. So basically, if you have a byte array and an int coming next, you can do write and read the other one, roughly. So there are a few exceptions to the rule, but treat it as UB generally. All right, perfect. We are out of time, right? So thank you very much. If you have more questions, you can grab me on the hallway. Have a nice conference. Have a nice day in Berlin. Thank you.